Hello, welcome to the next set of videos, 2.2 and 2.1. We're actually going to go back to 2.1 after I've introduced 2.2. So 2.2 deals with what's called the separation of variables method or technique to solve differential equations. And it's pretty much the standard thing you would think to do. So let's say you have dy dx, let's say, equals f of x times g of y. So you're going to do some algebra magic. Okay, and I'm going to say algebra magic because math students should be aware that what I'm doing here is sort of what we call just a formal manipulation. And by that I mean not every manipulation I'm making here is perfectly justified. And yet still it works. So we're going to go ahead and do it anyways. Okay, and then we're going to integrate both sides. Okay, so what did we do here? We went and we took and we brought this g of y here and this d of x here. So we get this equation, which is equivalent to this one. But like I said, this is a magical equation because we're not going to formally justify it. It exists, but we do have to think about it. Not at this level, we don't, but. Then we integrate both sides. And then the last thing we ask is, can we solve for y equals some y as a function of x? Okay, so that's our question. Okay, so there's a couple of things. This algebra magic, that's pretty easy to do actually, in most cases, that you can do this. This integration could be challenging. Gotta brush up on your Calc 2 skills with integrals. And then we ask, can we solve this? And this is gonna be basically college algebra level stuff on that last step, okay? So let's do an example, which is from 2.1. The velocity of a falling object with air resistance, okay? I mean, never mind, I was going to try to make that longer, but oh well. So, velocity of a falling object with air resistance, m dv dt, so that's mass times acceleration, right? Or, yeah, mass times acceleration equals mg minus bv. Okay, so here we're going to assume a couple of things. One, velocity is really, if we want to think of it as a vector, is going to be negative v in the, let's say, z direction. Okay, so it's just pointing down. Okay. So this velocity is automatically, this velocity that we have should be positive, the way that we're setting it up, because it's going down automatically. Okay. Another thing that we can assume, mg minus bv is greater than 0. Okay. So what are these terms? mg, this is your force due to gravity. And this term is your air resistance term. Okay, so air resistance in general is taken to be proportional to the the speed of your object. Okay, so now this has to be greater than 0 because it has to eventually point up or point down. It doesn't make sense that your air resistance is going to actually take your thing up. I mean, I guess with some like a leaf or something, you could imagine that it happens, but not in our object that we're going to be playing with, okay? So now let's take and solve this via separation of variables. So the only variables we have are v and t. So our independent variable here is t. Our dependent variable is v, and m, g, and b are taken as constants. Okay, so those are just numbers. We don't know what they are, but they're not variables. Okay, so now m dv divided by mg minus bv equals dt. Okay. One thing that I forgot to put up here is that there should be some constant, and we normally put it on the side of the independent variable. So when we do the integral here, okay, these are some pretty straightforward integrals, I hope, particularly on the right. If you can't do the integral on the right, then maybe we need to take you back to Calc 1. Okay, on the left is a little bit trickier, but still not too challenging. U is mg minus bv, so you're going to have m du over u divided by negative b. So your integral is going to be negative m over b, natural log of mg minus bv. And I don't worry about the c. The c went on the side of the independent variable. Okay, now the next question, can I solve for v? Okay, so now when you ask yourself that question, assume that you are good at algebra. Okay, now I'm assuming you are, you should make that assumption too. All right, so we make the effort. Don't just give up on it and say, oh, I can't solve for v because I'm stupid. No, we don't do that here. All right, so natural log of mg minus bv equals negative b over mt plus c. Now, I don't need to multiply the c by b over m. I'm just, because I mean, it's just still a constant. It's an unnamed constant. So if I multiply it by b over m, it's still going to be a constant, okay? Now, let's take the exponent of both sides. Now here, I'm going to say it's C0 e to the negative b over mt. I don't need that C0, okay? I could write C, but the thing that I want us to pay attention to is that taking the taking the exponential of both sides has changed how the constant comes in, okay? Right? Because if we did that, it would be like a plus c here, but that plus c actually went in as e to the c. So that's why it's now multiplying. Okay, just be careful on that. Now, we're going to go ahead and get v by itself. So negative bv is going to be negative mg plus c e to the negative b over mt. Okay, so v as a function of t is going to be mg divided by b minus c e to the negative b over mt. And there should be a, nope, I don't need this, the b, because this c is now this c divided by that b, okay? And really, I could make that plus or minus. Let's go ahead and make it plus. It doesn't matter because of the constant. Now, here's where things are going to matter. Assume we know v of time 0 is some v sub 0, okay? Assume we know that. Then v of 0 equals mg over b plus c e to the 0, which is 1. Okay, and that equals our v0 that we know. Okay, so v sub 0 equals, c equals v sub 0 minus mg over b. And now this is the c that's here, okay? Not on one of the previous ones, but this c. And now we can write our total solution is v of t equals mg over b plus v0 minus mg over b e to the negative b over mt. Okay, so keep in mind that, of course, the c has been changing all along. All right, we'll come back and do a couple more.